All right, thank you. So I'm going to describe simplicity, which we made an announcement about recently, and it is a next generation script language for Bitcoin and Bitcoin-like networks, which includes Elements and Liquid. So it's primarily the work of Russell O'Connor, but Andrew Polstra has been helping also since fall last year when we made a previous release, and Greg Maxwell has also been testing as well. So recalling Bitcoin scripts are predicates for spending coins. So your role is to, as the person who owns a coin or who wishes to spend it, is to cause the small program to return true, and then you can spend it. So simplicity is actually an elaboration of an idea described in some IRC discussions, as many Bitcoin-related ideas date back to from January 2012, when he was talking about MAST. And it turns out that more people are aware of MAST than simplicity, that actually the concepts for MAST were at that point already with the simplicity design in mind. So it's a fresh look at script design and focuses on provable security. So Russell has a PhD with the topic of formal security for programming and formal proof systems to assist in making verifiable software. And so Russell's been working on this full-time since almost 4 years now, since May 2016. Andrew and Greg, as I mentioned, have been working on it more recently. And we made a developer preview release last August, and the Simplicity Jets release, which we're going to describe now. So one new artifact of Simplicity this release is that it includes Jets, which we'll describe shortly. And this release also works on a Bitcoin branch as well as an Elements branch. And Elements is the open source platform, which is based on a Bitcoin code base with lots of extensions for confidential transactions, federated signing, asset issuance, and so forth. And the Liquid sidechain, which involves about 50 different exchanges and so forth at this point, is implemented using Elements. So that's a bit of history about the context. So simplicity relates to Bitcoin, and this release includes both a Bitcoin branch and Elements branch. So why is it interesting to think about simplicity? So Bitcoin scripts are constrained and security focused, but they have expressiveness limitations. And so what simplicity tries to do is to make the a replacement next generation Bitcoin script system, which is fully general, so you can program, generally arbitrary scripts and programs, and it introduces introspection so that you can look at the context. Bitcoin script today doesn't have introspection generally. Simplicity is very low level, so it's a kind of functional assembly language. So it's best to think of it as a kind of almost below assembly language that you would have on a CPU, because it's operating on bits and simple types and builds up even simple operations from those. We'll show a few examples in a minute. The point about having these very low-level operators is that the semantics are formally specified, and that it's a very small core language, so there are only 9 operators and some basic types. And the point about having formal semantics is that then everything's fully defined, and we can then use that as an input to be able to prove things about the script behavior in all conditions. Normally, when you're writing software, you test it in all the ways you can imagine using it. Maybe you try to fuzz test it, so try random things to see how well it performs. But with a formal proof system, you can prove things about how the scripts will behave in all possible conditions. So you can sort of make statements about how it will behave and then prove that that's always the case. One thing to bear in mind about Bitcoin scripts is that they are verification and not execution. So technically, when you cause a script to return true, you're not exactly executing the program. You are showing evidence that can be verified that you were able to execute it yourself, but the evidence you provide doesn't necessarily have to be executed by the verifier. So in particular with the masked concept, that means that if there are multiple OR branches, you won't execute ones that are not involved in being able to spend the coin, and you may not even disclose some of the script if you don't need to rely on that OR branch. And Simplicity relies on this heavily. So the top-level Simplicity program is a kind of commitment, like a hash of a tree of program snippets, and the branches of the tree are connected by OR statements. So you're going to navigate down the tree and pick one that you can cause to return true, and then reveal only that branch to the blockchain, and then the blockchain will verify what you claim and not necessarily see or need to know the rest of the program. Now, technically, Simplicity is not Turing complete, and this is intentional. So there's a concept, however, called post theorem, which shows that you do not lose expressive power because you're not executing programs. You're proving that they are able to return true. And so, contrary to some people's assumption, you don't lose expressive power by not having Turing completeness, because these are not execute programs. They're proofs of the ability to return to cause a function to return true. So some more about what Simplicity is. So it has access to an array of intrinsic functions. So as I described, the very lowest level is kind of assembly language, bit level machine. But from that are built a number of high level intrinsic functions. So things that would be inside the Bitcoin library or Bitcoin full node, lots of different functions. So all of those can eventually be made available as jets. So a jet is think of it as a kind of intrinsic function. If you implement things in the very low level, they will tend to be large and a bit slower because they're interpreted. So something that's going to be executed frequently, you might make a C implementation and then make a soft fork that replaces the Simplicity implementation with the C implementation, and you can then prove things about it. So you can prove that the C implementation is equivalent to the Simplicity implementation, and with the Simplicity implementation, you can prove its correctness and prove invariance about its behavior. So, as I was saying, that Simplicity uses the masked model, so you're only revealing the branch that you're using, and you don't necessarily need to reveal branches that you're not using. This is a bit like Taproot. So Taproot adds a one branch top level, and then the BIPs that go with Schnorr and Taproot also include masked, but that's in the context of existing Bitcoin scripts. This is masked in a Simplicity model. So we've, with the release that we did a few days ago, we include both an elements branch and a Bitcoin branch showing how Simplicity could in the future be added to Bitcoin if there was ecosystem interest, after people get to grips with it, understand the security properties of it, and so forth. So now we're going to go to some things about the operators and type system. So technically, there is not even kind of a Boolean type. So there's a unit type. The unit type is a kind of a type that has only one value. So if you think of a Boolean as something that holds a value 0 and 1, the unit type is something that just holds one value that's true. So it's a kind of very low-level basic thing. And then you have composition at the top right that lets you compose two functions. So a function S with input A and output B, another function with input B and output C. You can compose those two functions st so that you give it A, it calls the functions in turn and gives you the output. There's an inject left and an inject right, which are a way of composing types into tuples. There's a case statement, which is a kind of switch construct, and a pair, which is a kind of product. So to combine two types into a tuple with both of them in there. And then the bottom two are kind of like take the left from a tuple, take the left part, or drop, take the right part. So those are kind of like car and coulda, if you're familiar with Lisp. So using just the operators on this page, you can actually implement everything in a CPU, starting with a 1-bit adder, if statements, and building up to a 32-bit adder and so forth. And this next is showing the semantics. So if you understand the syntax, it tells you the semantics. So the identity function just returns its argument. The unit function returns a constant single value. Inject left and inject right are returning the left part of the tuple, the right part of the tuple. The case statement is returning the left part of an expression or the right part of an expression, depending on the type of the inputs. Pair is returning both function calls with that same argument in the take and drop I described. So you can see that it has some kind of low-level typing. The simplicity interpreter is operating on bit strings using these operators. So there's an interpreter that can execute this. So here's a Lisp-like syntax showing a half adder. So a half adder is going to add two Booleans, and it can have a carry output. So you can see using a Lisp-like syntax that you can define one of those. This is the simplicity binary for the half adder. So you can see it's got a kind of machine code level. The machine code is a canonicalized representation of the abstract syntax tree of the program. So here it is in diagrammatic form. So bear in mind this is a 1-bit adder, and here is an 8-bit adder. So you can see that the DAG gets larger, but nevertheless it's the same principle. You can notice that there's kind of reuse going on in here. So even though there is no looping, you have a kind of log scale reuse of snippets of code. So kind of if a section of code is repeated, it can just be reused without serializing it twice. So an 8-bit adder is made up of a 2-bit adder, a 4-bit adder, and so forth. So you can see the kind of structure in there. And of course, this is very small, so you can't read it, but this is the representation of a SHA-256 compression function, which includes everything, including 32-bit addition and the shift and all the other operators that go into that. They're kind of bit level things. So that is kind of give a bit of intuition about how simplicity programs look at the lowest level. And I wouldn't say a simplicity program is compiled. It's more assembled into a simplicity tree. And the reason we say that is because it's very simple. It doesn't involve any of the complexity that you would normally think about in terms of a compiler which is doing clever optimization of things. It's kind of straightforward process. And so in terms of the binary format, so what does a simplicity binary look like? It's a serialization of the abstract syntax tree. So when the binary is loaded into the interpreter, it reads the serialization and reconstructs the syntax tree, and then the execution proceeds by navigating the syntax tree using the input to the program. So the simplicity interpreter is called a bit machine. So it's an abstract machine with an execution model that's convenient for executing the simplicity program based on its tree structure. All the operators are executed using two implicit stacks. So implicit in the sense that you don't get to access them and program with them, but they're used internally to navigate evaluating a simplicity functional program. And there's a read and a write stack. So the elements on the stack are variable sized bit strings, because you're sort of composing larger and variable sized types using the type operators I showed. So you can think of it as kind of tuples of bits which have some type semantics. The bit machine executes this binary syntax tree. So on load, the binary syntax tree is loaded into memory, and then it's evaluated. So as I was saying, the interpreter is able to then evaluate those operators, process them while navigating the syntax tree, and end up returning true or false for the context of an output, like a Bitcoin or a liquid asset that you're trying to spend. So now some more things about. So the previous was, so this slide 12 here is trying to sort of explain simplicity more in the terminology that people would be familiar with from compilers and assembly programming and interpreters and so forth. And now we're sort of taking a step into a more specialized area, which is about formal correctness and tools people use and languages people use to describe systems with formal correctness and prove things are formally correct. So simplicity has a formal specification in a proof-assistant language for COQ. It's a general purpose proof assistant, and Russell has built three different bit machine implementations, so three different interpreters for simplicity, one written in COQ, one written in Haskell, and one written in C. And the COQ implementation has been formally verified, and I put this in bold because it's a very interesting and strong claim that most language interpreters don't have, and that is that the implementation is formally verified, so the interpreter is formally verified to correctly execute all possible simplicity programs. So that's a pretty interesting claim. And there's a path to proving security of C implementations of JETs and of the interpreter itself using the verifiable C project. So using that, it's kind of indirect. So we have this proof that I mentioned above about the generic correctness of the COQ implementation. And then to prove the C implementation is correct, you use the verifiable C platform and prove that the C implementation is equivalent, i.e. behaves in exactly the same way in all circumstances as the COQ implementation. And because of that, transitively, you end up with a proof that the C implementation is also will correctly execute all simplicity programs. And we can also prove other interesting constraints and behaviors about simplicity programs. For example, we can prove that it never overflows any safety bounds, like array bounds. We can prove how much maximum memory it can consume when evaluating a given simplicity program. So what does this provide in the context of Bitcoin or elements or Bitcoin-like blockchains? So one thing it allows you to do is to implement new functionality, even low-level functionality, without needing a soft fork necessarily. So the Schnorr digital signature algorithm, which there's a BIP for now, so presume over the next this year or next year, there will be steps to try and add that to Bitcoin. If Bitcoin had simplicity today, you would be able to implement Schnorr in simplicity itself without needing a soft fork. So it shows the generality of simplicity in terms of its expressiveness. So other examples include, there's a particular sort of softworks extension which is desirable for Lightning called Sidechains no input, or there are some other alternatives. And so that would also at some point need to become a soft fork for Bitcoin for Lightning to work more efficiently, the L2 version of Lightning. But if Bitcoin had simplicity today, you could implement no input directly in inline. You wouldn't need a soft fork. So now if you do that, the program size, simplicity is surprisingly compact. The example I showed of the SHA-256 is only a small amount of kilobytes, but to get things smaller, we implement things as jets. So then there'll be C implementations of common functions, and that means that something like sighash no input with access to a common library of jets, i.e. C implementations and proofable equivalents to their simplicity implementations of the same functionality, we can implement quite compactly a range of things directly without needing to soft fork. So the generality means you can build a lot of different things. So to give some concrete examples that people have discussed as interesting and nice to have Bitcoin functionality, include the sort of time lock vault feature, where you would, instead of storing Bitcoin on a simple UTXO, where it can be spent if you have access to the private key, with a vault you have access to a private key, but it's restricted in what it can do. So it can only initially give notice that it intends to spend the coin after a time delay. So let's say after a week, and during the notice period that can be cancelled. So it gives you some protection, because if the private keys are compromised or stolen from a safe or something like that, somebody can notice that and cancel it if it's not authorized. You can also build velocity limits directly into the storage scheme so that you don't have to have a distinction between a hot and a cold wallet and rebalancing. In Liquid, there's something called a liquid swap tool, which is a way to trustlessly do an atomic swap of, let's say, 1 Bitcoin for current price of Bitcoin in US dollars using a stablecoin like Tether. Using today's Liquid script, which is essentially Bitcoin script plus a few extra opcodes, it's a little difficult to do more than a full match. So you have to sell a whole Bitcoin. If somebody wants to buy half a Bitcoin, they wouldn't be able to do that without somebody providing the extra liquidity. So with simplicity and its expressiveness, you could do a partial match as well. So you could use a kind of covenant-like construction to do a partial match and be therefore authorized to create a new transaction that has the same offer with the remainder of the transaction that's offered for sale. And you can do these things with the ability to prove things about their behavior, so constraints or things they will do in all circumstances, or the only way that this can be spent is if this claim is true. So here's some data about the jets that are in this release. So there are more jets coming, but there's a SHA-256 compression function and a verifiable C proof that it's correct and equivalent to the simplicity version is equivalent to the C version. There are jets for 32-bit arithmetic, and there's a jet for the Schnorr signature, which includes, all of the elliptic curve library aspects that verify Schnorr signature, which is similar to an ECDSA signature, and more jets will follow. So, in particular, what does that do? So, if we compare the simplicity without jets, in a previous release, we did a version of Schnorr in pure simplicity, and that took 11.5 minutes to execute and was 13.6 kilobytes big. Now, that sounds large, but it's actually quite impressive because it included everything from the bit level up, including the SHA-256 implementation, a big number library, 32-bit arithmetic, and elliptic curve library, and all of the serialization to serialize a transaction and hash it so that it can be verified. So if you can compare that to ECDSA, kind of boilerplate to make an ECDSA signature is 25 bytes. And with the release that we did this week, the Schnorr in simplicity with jets is 448 bytes. So you might wonder, why is it bigger? And the reason it's bigger is that what's jetted is the the Schnorr crypto operation, but not the serialization. So most of those 448 bytes are to do with serializing the transaction and satisfying the Schnorr mathematical relation plus the the public key and the signature, the raw signature. So with more jets of the serialization, the size would basically be the same as ECDSA. And already you can see that the performance in evaluation time is much closer. So it's slower, but that is primarily because of micro-optimization and because of the interpreted serialization. So I think, so apparently there are some questions, so we could switch over to questions for a second. And Russell is in the chat as well, so if you see answers from Russell, they are the kind of definitive answer. Wow, there's a lot of questions in here. So the Turing completeness discussion we mentioned. So Bob McElrath asks, can this be used with Bitcoin? Like, how can it be used with Bitcoin in this release? Is it reg test only? Yes, it's reg test only. And there is some kind of limitation, which we'll get onto in a bit, where the full version would probably use a different script version number and maybe move across to Taproot, because Taproot has a more flexible versioning system than SegWit, which it's using today. So if you click on the question tab, you'll be able to see the questions. So in the case of simplicity being enabled on Bitcoin, does it provide assurances or guidance to a user using equivalent of no input? Okay, so this is a kind of power versus risk question from Michael Folkson. So I think the point is you can maybe think about a couple of different levels of simplicity. So one level is a very low level programming, which is arguably best used by kind of library, like system library writers. So somebody who understands the internals to build something that is safe and then have people use that. So, it's possible to write unsafe Bitcoin scripts today where, by accident they can be spent with opt-true or something. And so this kind of risk remains. So you do have to be careful. So it's a kind of, with great power comes great responsibility. So you have to be careful that the script template you're using has been, verified and understood by people who are understand the internals quite well. So yeah, it doesn't, so one of the controls today is that these soft forks have been kind of designed to minimize risk or to provide warnings and things. So this is a kind of level below. So I think, in practice, you would, have more library validated intrinsics or library level things. And so, people need to be careful about what they put money into, but it's, an existing wallet wouldn't output a script that it doesn't understand. So, for example, one gate is that wallet authors would have to form an opinion about a script. So in the example with no input, that's primarily of interest to Lightning. So people with low-level knowledge of Bitcoin and Lightning would, have a discussion about the best semantics for no input and then implement it and use it in a Lightning spec, and then people could start adopting it. So there's a question about fees. Yeah, so there's some things we're going to talk about in a bit about fees. So there does need to be a fee, more thought put into a fee model for scripts, for simplicity scripts, and with jets, they get implemented as a soft fork, so it becomes possible to, have a cheaper, lower byte count, lower CPU overhead way to do the same thing, where if you were to do it just as a simplicity program, it would have a larger cost. So that, part of soft forking in a jet would be evaluating what a sensible and safe fee cost for it should be. Okay, so I guess we'll switch back to can you see the so I'm going to switch back to the slides. Okay, good. So right, so we described the kind of space saving and runtime aspects here. So I think the point is that the runtime performance is quite good. The, for if you're writing very low level things, you might need to jet them. And the if you're writing sort of general application things, you may not need to jet them. You could just use them, because interpreting a small program with extensive use of jet intrinsic functions is pretty compact and will be interpreted fast enough. So that gives you the kind of ability to do things more rapidly without waiting for sort of standardization of soft fork. There is a kind of, there are more details to work out, but in principle, it would also be possible to do something which is kind of a little bit like a jet, but without a C implementation. So rather than, because bear in mind, when you are calling a simplicity program, the program is inlined, so that not all of it is necessarily revealed, but the hash of the program is attached to a Bitcoin or an asset. And then when you spend it, you're revealing some branches of the program and the inputs to make it return true. So if that is, a small program and it's frequently used, you could potentially sort of save it. So pay a cost for a special type of UTXO, which is the sort of macro of that program, and then save kind of on a network level and a storage level some of the overheads, but you would not be able to change the fee cost, because that is that's difficult to do without having a soft fork and a new opcode. But it would sort of be a network and disk compression option for frequently used small programs. So that could be explored also. So now another question is, what's needed for simplicity on Liquid? So as you see in this release, there is simplicity for elements. And elements is the underlying toolkit that simplicity is built with, that Liquid is built with. And some people have run other blockchains using elements. You can run your own blockchain. So this elements branch is a kind of precursor, and we'll improve it, and that will become the basis for adding simplicity to Liquid, which we're targeting for later this year. So what's needed for that? So one thing, as I mentioned, Taproot. So Taproot has a more flexible update and version system than SegWit. So we are intending to integrate Taproot into Elements and Liquids, possibly ahead of it being in Bitcoin, depending on the timing, and then adapt simplicity to work with the Taproot script version. We've also got to implement a cost model to take account of jets. So this is a question about fees and jets and how that works. There are some more completeness things. The core of simplicity is complete in terms of the interpreter functionality and the ability to evaluate things, but there are some pieces that are missing. So resource estimates of the execution time and memory of features, some anti-denial of service improvements. There is a binary format, but we may want to finalize one that we're going to commit to keeping binary compatibility with. A lot more jets and proofs of equivalence to simplicity programs, or the simplicity version of the jets. So more proofs, more jets, so that there's a quite wide library of jets composed of common things that are used at the next level down inside Bitcoin full node. There are lots of helper functions in the code base that would be convenient to gain access to write simplicity programs in a compact way and in a convenient way. So another big area is developer tooling. So we're going to show some command line demo that of the current release on Bitcoin that Russell put together and explain what's going on there. But the developer tooling is missing, or very basic at this point. So it's a bit more like machine code than like assembly programming. And so one direction we're interested to go there is to extend Miniscript. So Miniscript is a sort of layer above today's Bitcoin scripts, which expresses them in a more logic-based grammar instead of the kind of stack machine of looking at raw Bitcoin scripts. And Miniscript is both compilable and decompilable, so you can express your intended behavior and then compile it into Bitcoin script, and you can decompile a Bitcoin script and have it explained in Miniscript language. And there are two languages involved. So Miniscript's a separate project. You can use that today on Bitcoin. You can go look it up. So we're intending to extend Miniscript to add some simplicity-enabled functionality. So we'll pick some subset, hopefully with powerful and useful properties, extend Miniscript with that, and then for that extended Miniscript, you'd be able to then compile that down to simplicity and have the simplicity assembled into a bit machine binary. And then we need more developer tools and more documentation. So I think at this point I'll switch to the Russell's demo. So I need to switch to screen sharing to another window here. Okay, so now this is a recording using an ASCII thing of Russell showing some of the command line things you can do, or that he did. So I'll try and explain it. And so basically it's using a simplicity package for Haskell. So he's starting up the Haskell toolkit and interpreter, loading the simplicity package. And here you can see he's calling a Bitcoin raw transaction. So the exclamation mark syntax was calling a shell script, like a command line from within the Haskell interpreter. And so this is the Bitcoin transaction, and the hash at the end there is a kind of P2SH of a simplicity script. This is what I was mentioning with Bob Makara's question, that -1 is the SegWit version. So we're going to switch it to use the Taproot version when we get to integrate Taproot into Elements and Liquid. And if it was integrated into Bitcoin, of course, Bitcoin is a moving target, but that seems like a better way to do things for Bitcoin purposes as well. The program is sighash, and Russell's now sort of typing helper functions and Haskell to show things. So there's a function that serializes a simplicity extraction into a binary format. So basically, he's showing you sort of internals of some Haskell library and manually constructing simplicity binaries. So this is where there's a comment in the Medium post that this is a kind of very low-level manually crafted script. So he's crafting it using the simplicity package for Haskell. The signature above he computed somewhere else, I think actually in Sage, which is a mathematical package that understands elliptic curves. So he made the elliptic curve signature, cut and paste the hex in, and there he made a simplicity binary. And then we're going to parse the binary so that we can kind of decompile and show things about it. So he's going to show some hex. of the parsed binary. And there you see the commitment, which is the top level of the simplicity binaries parse tree, or the mast. And then he's going to save the binary to a file so that he can then create a transaction with it and so forth. So obviously what needs to happen above this is, more easy to use RPC commands and command line tools and all that kind of thing. This is the kind of next level down. So that's where I was saying that we need more developer tools. There is a decompilation, or the hex of that. So the last bytes are the witness, and the signature. So bearing in mind, so he's going to try and spend it basically. So you have, because it's P2SH like, you have to provide the script as part of the script signature. So the witness that we sent in includes the whole simplicity binary, or the section of it if it has OR branches that we need in order to spend it. And now he's going to disassemble it to show that the binary can be parsed into its component parts and show something about what it looks like symbolically. So it's going to give you a text representation of the opcodes that we showed at the beginning, and organized in a tree structure. So this is a pretty printer that he just typed, a very simple one. And then we'll see in a sec the disassembly. So here you see all of the simplicity combinators. There are 196 starting at 0. So these are all the little kind of bit level and bit string operations. And you can see some jets in there. There's a SHA-256 compression jet, which is taking a bit string off the stack and calling a compression round. And also the Schnorr verification jet. So the simplicity program is reading the transaction data, hashing it, and then verifying it using the Schnorr signature. It's another section of disassembly. He thinks that's the public key. And right, so the other point is that these, so in answer to the question, we can make the .cast file available. So this program is 448 bytes, but it will become much smaller, converging on the similar size to a Bitcoin ECDSA sort of template, which is 25 bytes, as more of it is jetted. So as I was saying, the part that is, just switch back to the slides. Yeah, the part that is large at the moment is the serialization and all the calls to the low-level operations to construct the data, serialize it together, and then hash it, and then finally call the Schnorr verification jet. So in terms of what comes next, So we are continuing development on Elements. The initial developer preview we made was last September, and the Simplicity release with Jets that we were just discussing on this presentation. We're targeting availability of this in Liquid this year. I would say late this year, like that's a lot to do. And as you can see from the availability of a Bitcoin branch as well, that Simplicity is compatible with Bitcoin. It was actually designed, long before Elements and even sidechains as a concept back in 2012, but in active development since 2016. So it's almost 4 years now. And the idea is that basically we can, prove things out in Liquid. So add it to Elements, add it to Liquid, allow people to try it out in that context. Obviously, if you're very familiar with low-level intrinsics, you might be able to do things with the current reg test release and playing along. If you ask questions on the Elements IRC or Bitcoin Core Slack. And so the idea is that later it would become an interesting candidate BIP for Bitcoin, but bear in mind this is probably a few years down the road, and there are kind of lots of technical questions that have to be validated about how to do this safely in practice. So there are some precedents for things being tried in a sidechain before. So, for example, a precursor to SegWit was tried in an early version of Elements. There was a previous version of Schnorr in an early version of Elements, and so there's sort of been preview versions of things in the sidechain, maybe 3 or 4 years. Well, 2 to 4 years before they've come into Bitcoin historically. And so we'll have to see. Obviously, Simplicity is a pretty large and complex change, but there may be sort of sandbox or container concepts that could be put around it to improve the safety. So that's the end of the slide presentation. And I guess we can switch back to the question and answers. So a question about Miniscript. If you can use Miniscript, you should use Miniscript rather than Simplicity. So the reason is that it's a kind of higher level language, right? So if you think about writing something in assembly language versus, writing something in Python or something like that, then Miniscript is a way to state things intentionally. So it's much higher level, but it doesn't give you access to the full expressiveness in the case of Simplicity. So we would, add more functionality over time and sort of grow Miniscript into a high-level language with an intentional way to express script programs and constraints. So we'll have to see how far that can go, and maybe there's room for other high-level languages that can also compile into Simplicity. Certainly you could compile today's Miniscript into Simplicity because that can be compiled into Bitcoin script already. But the interesting thing is, what new functionality, for example, could we add covenants to Miniscripts? How do you express covenants in a intentional way? So there are lots of questions about how you would do things. So we just start and then build up from there. So a high-level language like Ivy, yeah, that's certainly an interesting thing to have compile into simplicity, and maybe Ivy itself could be expanded on and compiled down to simplicity. So there's room for kind of multiple languages to compile down to it. Basically, it's a kind of functional language with access to lots of intrinsics. Plan for tooling to work with multi-transaction covenants. So I think you could safely typify simplicity as a bottom-up approach to the world, and Bitcoin itself, I think, personally, is kind of bottom-up, right? There's the sort of robust things that work and then build upwards from there. So I think you would want to just start with a covenant mechanism, and then some safe way to bind multi-transactions together to do things sort of high level. I mean, there has been thought in the past to having sort of intentional high level toolkits to sort of compile this protocol descriptions, like a Lightning protocol, into a language and then down into an interpreted language. So, conceivably, but that's a couple of levels of high level language design removed. So as it's possible, but it's something that would need work, and could be pretty interesting because it could speed up the sort of time from protocol ideas into availability. I think the other interesting thing would be to preserve the security guarantees and the semantic analysis for these multi-transactions so that you can make statements about how they will behave in all circumstances. So any more questions? Okay. Then I think we will, as Daniel mentioned, upload the video and the cast file. The other materials are online. I guess we can make the slides available too if you want to see them separately. And the other references are available. So I guess we'll wrap up there. Thank you everyone for attending, and I hope it gave a flavor for how simplicity works. And I think for kind of ongoing Q&A, the Bitcoin Core Slack with elements, or there's an IRC channel which it's equivalent to as well, which you can find. So those are probably the best places. There's also a tech discussion chat on Core Slack, which I see that Russell is in sometimes. So you can ask generally technical questions. So, thank you.